What I'm going to be talking about is a bit of a theory, mathematics, meteor astronomy. It was inspired by two projects, one of which was, in fact, my doctorate thesis, which I graduated this year. It's not about strawberry jam or anything, because it looks like this. It's, in fact, the kernel density estimation method around the meteors as observed by our M scales. And the second method will be about kernel smoothing, which will be applied to all sky reduction of residuals of our Ames cameras. So to compare parametric and non-parametric methods, I believe most of you have met all of them. Usually when we are trying to do something with our data, we try to fit our data set with a known function. So we assume there is a closed form underlying law to something, and we try to fit by some function using the least square method or something similar, or to try a Fourier or Taylor or some other kind of expansion to find a coefficient that will describe our data set best. This is arguably much simpler. However, we impart some preconceptions into our data. So sometimes this is not exactly good. Non-parametric methods, they so-called let the data speak for themselves. In this class, we have histograms, which I personally don't like very much, interpolation methods, and the two methods I will be talking about, kernel density estimation and smoothing. This is much more complex and much more difficult to share, especially your results are not describable by several numbers. However, it just looks better and sometimes gives you some insight you are not able to gain using parametric methods. So with kernel, the basic idea is it's not the sunflower kernel. The basic idea here is to replace every observation with a fuzzy version of the function, which is shaped as some kernel function, usually a normal distribution or something like that, scaled to some predetermined bandwidth h. Effectively, in kernel density estimation, this is a convolution. I will not go into mathematical details. The example here is simple. We have here 5 data points. We replace each of them with a normal distribution and sum them up. Suddenly, we have a compound distribution that should describe our estimate of the original distribution from which these data were sampled. Here, kernel shape is not that important. It is, but it's not the crucial thing. We can choose from a variety of functions. Usually, we just use the normal or so-called Stefanich-Nico kernel. So this is a truncated parabola. What is crucial is the bandwidth. So this is the width to which you scale your kernel. The simplest method is to have it fixed, to estimate it somehow, or just take it from data as well. For instance, take k nearest neighbors of each data point, find the distance to k nearest neighbor, and use this as your bandwidth. If you have multidimensional data, you want also to include covariance. We'll get to this shortly. So our first application, this was actually my thesis, was a model of meteor activity. Again, if you want to model meteor showers, you might want to use the parametric methods. Two of them are, for instance, the Kurpale stream model, where you have the beginning of the meteor shower, the duration, the attack and decay angles, and maximum activity, or the model by Peter-Yanni scans, where you have solar longitude, velocities, and position of the radian and its movement over time, and so on. If you want to use the non-parametric methods, in the KDE, you have to determine the relevant parameters as well. Then you have to design a function that says how dissimilar are two meteors, be it two real meteors or a real meteor and a virtual one. If you want to get the probability function for a virtual meteor, so the probability that a meteor with these properties will appear at this time, position, space, and so on. Next, you have to find suitable bandwidth, run the simulation, and verify. Why the concept of covariance is also important can be easily shown in 2 dimensions. Of course, we have many more. So if I determine the bandwidth to be, I think this is the 20th nearest neighbor, I will get something that is very fuzzy on the edges. So in reality, well, my hands are shaking, but here you have something that is not 0. However, it's virtually impossible for a meteor to appear here. I can do something with it. I can use a narrower bandwidth. However, soon this decays into a set of disjunct circles or blocks. However, if I include the covariance, so here this is clearly correlated. In any point except for the center, we can see that this is either this way or that way. If I include the data in the bandwidth selection, I no longer have circles, I have elliptical blocks. And if I overlap them or just sum their contributions, I suddenly obtain something that is much more precise and much sharper. So the relevant parameters here, meteor observations. Of course, this can be recorded extremely precisely, especially for our purposes, 1 second is plenty. Position, well, not in fact position, because position is dependent on the position of the observer. What doesn't change is the radiant. So this is two properties, the radius extension of declination plus the speed component. And finally, for meteors, not meteoroids, is the absolute magnitude. So we obtain a 5-dimensional space. Meteor is described by a single point, is this 5D space. And what we're trying to do is to estimate the probability that a meteor with this set of combinations is bound to arrive at some time. So to cut it short, because my talk was shortened by 5 minutes, I had to throw some mathematical stuff out. I bet you regret it already. Start with the simulation or this KDE on our Amos database, just a preliminary one from 2016, I believe, from 2 stations at Canary Islands in Slovakia. We obtained the reduced global probability distribution function for Amos. Here in coordinate the radius extension and declination, and time component has been cut out. I have a video with me, so at the end of the talk, I will show the full version of this. So some measures are better left on this term, so we want to keep time as time only compresses to seconds. The second thing I'm going to be talking about is a virtual plate corrector, which I find it very lucky that Mike was talking about something very, very similar. I propose a method for correcting this. So our common problem in astrometry is that we have an optical path that is never perfect. We have, in particular with Amos, we have an image intensifier, a fisheye lens, a chip, and well, whoever has seen the innards of the device knows that it's pretty difficult to get it all right. So the zenith position is usually not absolutely correct. It can be rotated around the vertical axis. The scaling and other distortions introduced by the optical system are all there. Currently, we're using the formulae by Dr. Bogovička from 1995, which try to fit 13 constants. And if we do this, we are left with residuals which look like this. So there is an image of, I don't know, approximately 100 stars and exaggerated vectors of displacement. So basically the difference between the cathode position and the observed one. So our task, mathematically good, is that we are given the observed position of stars on the chip, which can be reduced on the unit disk, so not in pixel coordinates, but unit coordinates, and a catalog. And we are going to try to find the error, which can be at the position of stars is determined as simple subtraction or difference of them. For every star, we just reduce it from celestial coordinates to local coordinates, to chip coordinates, and unit coordinates. And for meteors, we do basically the same. Only the distinction is that we do it in the opposite direction. So the solution to this, when I was tasked to do this, was to try to interpolate, because we want the function to be contiguous over the entire domain, over the unit disk. So we assume that our measure data is exact. So when we see a star, we know that this is the star and it's displaced by a few, I don't know, hundreds of pixels, or maybe at most 1 pixel. A huge problem is there is which when the stars are not identified correctly, of course, this really breaks the whole thing. And another problem, not that might just a huge one, is that if there are no data near the edge, which is usually the case, of course, near the horizon with an all-sky camera, we need to extrapolate as well. This is not very lucky because, well, you know, that extrapolation usually carries very huge errors. So if I do this, in Python, I just naively interpolate the vector data over the entire unit disk. I obtain something like this. And now if I have meteor that passes through covered area, I'm able to subtract the probability, obtain something that's supposed to be much better. Second thing is that I can interpolate, extrapolate again, just to use in the area that is not covered. I can use the nearest neighbor algorithm. So I just sort of extrapolate with a constant value in each radial in each direction, all the way to the edge of the field of view. Of course, this is not guaranteed to be entirely correct, but is one of the best things I'm able to achieve with the data I have. What I had in mind then, and what I found extremely interesting for a theoretically based person like me, is the polynomial expansion of Fritz Zernike, the winner of the Nobel Prize in physics in 1953 for something completely unrelated to this. He devised a set of polynomials defined over the unit disk. that form a complete base. So each smooth function can be written as sum of Czerny polynomials with some coefficients that can be determined simply by taking the inner product. Again, I'm going to bore you with the mathematical details. They look like this. So the simplest one is just a constant function, and then just grows more and more complex. Most of you have probably already met them. If you have a telescope, they correspond to various aberrations, so comma, trefoil, and also the elastic mechanism. So each one of them corresponds to one of the Czerny polynomials. Usually you encounter the maybe what's in the picture, so the first 15 or so. Again, there's an infinite number of them. So how is this related to what I'm doing? Well, Zhao and Birch have shown that you can also extend these polynomials to vector forms. So you are able to expand any vector function into a set of gradients of Czerny polynomials. And what is again very lucky is that if you take the gradient, it can be expanded in terms of scalar Czerny polynomials. And if you use linear combination of at most 4 of them, you can put them together and obtain a function that is one of the polynomials. We have 2 categories. Some of them have no rotation, some of them have no divergence, and some of them have neither. So usually it looks like this, some combination of all the scalar ones. Here's a brief glimpse into the zoo. So there are some of them. You can see that, for instance, here, everything wants to go from there here. Here you can see the trefoil pattern, double rotation pattern, and so on, so on. I have a backup slide. If you're interested, I can generate these along to do in Python. First of all, our problem is here that to be able to expand, to find the expansion, we need to not only interpolate, but also extrapolate our data. And when we saw the original image, we could see that while it's continuous, its derivatives are not, because we are extrapolating using near the neighbor, so we get a sort of a flat profile towards the edge. So what I tried to do is not to interpolate the data, but smooth out. So the error function doesn't have to be 0 at the positions of stars, which is in fact good because we have incorrect identifications, or we can have something that is simply noise. So at every point, we will not interpolate, but compute a weighted average of all observations. And to employ a kernel method, we will use kernels to measure volt strength. And volt strength of each measured point will be decreasing with distance like this. Again, this is very simple, a simple weighted average based on distance. So we are left with this. We can see that this is smooth. This is smooth even in higher derivatives. So for instance, here we only have 1 data point, and we hope it's been correctly identified. This is exaggerated by a factor of 50, so this should be probably 1 pixel or maybe 2 pixels at most. And we see that in this region, everything wants to go southwest or southeast because the whole sky cameras skipping up. Here, the vote is on animals that everything wants to go up. And here in the middle, we see that we are already reduced basically to noise. So these are just random components, random measurement errors. Initially, I had a slide with the Czerny expansion of this, but just last evening, I realized it was not entirely correct, so I left it out. So I skipped straight to the overview, but I hope I will be able to produce a correct one during the conference. So to summarize, kernel methods, I found them to be viable and often much easier alternative to classic methods, also much more precise. And I find that it's much easier to provide approximations where a simple extrapolation would almost certainly fail. And now I would like to show you the video of the Amos dataset. Here from smartphone, and here you can see all the showers that they have captured. So this is the birthdays, which is approximately 140. I believe these are the Geminids, the Taurid complex, and everything. Can we look a bit?
Just want to share with Zoom.
Yeah, sure.
As well.
So you can see that today is very high maximum. The Halton complex is 10 minutes and a huge void here. Well, most of the time because we don't have enough hours. So, thank you.